I want you to forget everything you think you know about distance for a moment, because the problem begins with a number that sounds harmless. 1 light year. It feels manageable, almost modest, like a stepping stone astronomers use before moving on to something truly impressive. You hear millions of light years, billions of light years, and the single light year quietly shrinks into the background, reduced to a unit so small it barely deserves attention. But this intuition is completely wrong. 1 light year is not a convenient measuring stick. It is already so vast that it pushes human imagination to the edge of failure. And the only reason it doesn't feel that way is because the number itself is too large for the brain to process emotionally. A light year is the distance light travels in 1 year. And that definition hides the brutality of what it actually represents. Light moves at 299. 792 kilometers per second. Not approximately, not roughly, but exactly, a fundamental constant woven into the structure of space-time itself in a single second. Light circles. Earth more than 7 times. In 1 minute, it crosses nearly 18 million kilometers. In 1 hour, it travels over 1 billion kilometers. Let that continue, uninterrupted, for a full year. Every second stacked relentlessly on top of the last, and you arrive at roughly 46 trillion kilometers. The number is so large it becomes abstract, stripped of weight, something you read and acknowledge without ever feeling its scale. So instead of digits, imagine something more familiar. The distance from Earth to the Moon, the farthest any human has ever traveled, is about 384. 400 kilometers. Apollo astronauts needed roughly 3 days to cross that gap. And when they looked back, Earth had already shrunk to a fragile sphere suspended in blackness. Now stretch that journey end to end, not 10 times, not 1,000 times, but roughly 25 million times. Stack each 3-day trip consecutively, launch after launch, century after century, until the chain finally reaches 1 light year. The total travel time at Apollo speed would exceed 200,000 years. That is longer than the entire span of recorded human civilization. Even the scale of our solar system offers little comfort. The average distance between Earth and the Sun defines 1 astronomical unit, about 150 million kilometers. 1 light year contains more than 63,000 of those units. If you lined up the entire solar system, sunto Pluto, you could repeat it over 1,600 times before filling the gap of a single light year. Everything humanity has ever explored, every planet, every moon, every probe, exists inside a region that becomes almost microscopic compared with that distance. Try shrinking the solar system to something you can hold. Imagine the sun as a marble on a table. Earth becomes a tiny grain of dust, orbiting about 1 meter away. Neptune sits roughly 30 meters out. The size of a peppercorn at the end of a basketball court. Now extend that scale to 1 light year. The next star would not be across the room or even across the city. It would be tens of kilometers away, far beyond the horizon, separated by nothing but emptiness. No planets, no markers, no structure, just vacuum stretching across a distance that, even in miniature, refuses to feel connected. This emptiness matters because the space between stars is not merely large, it is almost perfectly void. The interstellar medium contains roughly 1 atom per cubic centimeter, trillions of times less dense than the air you are breathing. There are no gravitational shortcuts, no refueling stops, no natural pathways. Crossing 1 light year means carrying everything with you across a desert more absolute than anything on Earth. The distance is not just long, it is isolating. Ciel, and indifferent to the traveler attempting to cross it. The most distant object humanity has ever launched, Voyager 1, has been traveling since 1977. After nearly half a century, it has covered only a tiny fraction of 1 light year, less than 1% of 1%. If it were aimed at a destination 1 light year away, it would need tens of thousands of years to arrive. That is not a failure of engineering. It is a direct consequence of how enormous this single unit of distance truly is. 1 light year is often treated as the smallest meaningful step between stars, yet even this first step already dwarfs everything humanity has ever done. It transforms exploration into endurance, communication into delay, and distance into a barrier measured in centuries before discussing engines, fuels, or ambitious missions. The scale itself quietly establishes the terms of the problem, and those terms are far more demanding than intuition ever suggests. What makes 1 light year truly unsettling is not only its size, but the nature of what lies inside it. Human beings are used to distance as something that can be crossed through landscapes, along roads, over oceans, or through air, always with the assumption that the space in between still belongs to the same world we know. Interstellar space breaks that intuition completely. The gap between stars is not a route. It is not an environment in any familiar sense. It is an emptiness so severe that it strips away nearly every advantage our machines have ever relied on and reduces travel to a prolonged contest with isolation, inertia, and delay. The interstellar medium is often described as a vacuum, but even that word can sound milder than the reality deserves. In the space between stars, matter thins out to roughly 1 atom per cubic centimeter. Compare that with the air around you, which contains something like 25 billion trillion molecules in the same volume, and the contrast becomes almost absurd. If you tried to recreate interstellar conditions on Earth, you would not just empty a room of air, or a building, or even a city. You would be trying to simulate a level of absence that ordinary human experience never encounters. A stray hydrogen atom here, a microscopic dust grain there, and otherwise almost nothing. No atmosphere to break against, no nearby planets to exploit for gravitational assists, no natural checkpoints, no sources of fuel waiting in the dark. A spacecraft traveling across 1 light year would move through a region that offers essentially no help at all. That matters because nearly every mission humanity has ever flown has depended, in one way or another, on the structure of its surroundings. Orbital spacecraft use gravity constantly. Interplanetary probes borrow momentum from planets through slingshot maneuvers. Mars missions rely on atmospheric entry systems. Even our greatest deep space missions were designed around a solar system rich with intermediate bodies, each one acting as a stepping stone or an anchor point. Remove all of that and replace it with 946 trillion kilometers of near featureless emptiness, and the character of the journey changes. Every joule of energy, every correction, every system needed for survival or communication must come from the vehicle itself or from a distant source back home. There are no rest stops in interstellar space because there is almost nothing there to rest beside. Voyager 1 makes this reality painfully concrete. Launched in 1977, it remains the most distant human-made object ever sent into space. It passed Jupiter, then Saturn, and continued outward until it entered interstellar space, becoming a symbol of human reach. Yet after more than 4 decades of travel, it has covered only a tiny fraction of 1 light year, about 0.0027 light years That means the farthest object our species has ever placed in the cosmos has not even crossed 1/3 of 1% of the distance under discussion. If Voyager 1 had been aimed at a target exactly 1 light year away and continued at its present speed, it would need roughly 17, 0, 0, 0 to 18, 000 years to arrive. That span is longer than the time separating us from the end of the last ice age. At that point, distance stops behaving like distance in the ordinary sense and starts behaving like time. A probe halfway to a 1 light year destination would already be separated from Earth by a 6-month signal delay in each direction. A message sent from mission control would arrive half a year later. A reply would take another half year to come back. Real-time control disappears. Conversation disappears. Even relevance begins to disappear, because any information exchanged belongs to a past that keeps receding while the spacecraft continues forward. The deeper implication is not merely technical. A ship in transit is not only far from home, it is increasingly out of sync with home, living inside a different rhythm of cause and response. Seen this way, interstellar space is not just a larger version of the solar system. It is a different condition altogether. The vacuum is thinner, the support is gone. The delays grow long enough to reshape decision-making. And the best example of human reach still falls so far short of 1 light year that the scale becomes impossible to ignore. The numbers do not need dramatic interpretation. They are already severe enough on their own. Interstellar distance does not defeat us because we lack courage or imagination, but because every engine humanity has ever built operates in a velocity regime that is almost irrelevant compared with the scale of a light year. The rockets that carried astronauts to the moon, the probes that crossed the solar system, and the spacecraft now drifting through interstellar space all rely on the same basic idea: throw mass backward to move forward. This principle is simple, elegant, and devastatingly limited because the relationship between how fast you want to go and how much propellant you must carry is not linear. It is exponential, and that exponential penalty is encoded in what engineers call the rocket equation. A chemical rocket works by burning propellant and expelling hot exhaust through a nozzle. The faster the exhaust leaves the engine, the more momentum the rocket gains. The best chemical engines humanity has built, burning liquid hydrogen and oxygen, achieve exhaust velocities around 4 kilometers per second. That number is impressive by terrestrial standards, but compared with the speed of light, nearly 300 kilometers per second. It is microscopic. This disparity is where the rocket equation becomes unforgiving. The equation states that a rocket's achievable change in velocity equals the exhaust velocity multiplied by the natural logarithm of the mass ratio between the fully fueled vehicle and the empty vehicle after propellant is spent. Because the logarithm grows slowly, adding more fuel produces diminishing returns. Doubling fuel does not double speed. It barely nudges it. Imagine a spacecraft with a 1-ton payload aiming for a modest speed of 10 kilometers per second. With chemical propulsion, the required fuel mass is manageable. Perhaps 10 times the payload push the target speed to 20 kilometers per second, and the required fuel increases dramatically. At 40 kilometers per second, the vehicle becomes mostly propellant with a tiny payload at the front. Attempt 100 kilometers per second. Still only a tiny fraction of light speed, and the fuel requirement becomes absurd. Billions of tons for a 1-ton payload. The mathematics does not bend to optimism. Chemical propulsion simply cannot reach velocities meaningful for interstellar travel. Even our fastest spacecraft, assisted by planetary gravity, leave the solar system at around 15 to 20 kilometers per second. At that speed, crossing 1 light year takes more than 10,000 years. Naturally, engineers turn to nuclear energy. Nuclear thermal propulsion replaces chemical combustion with a reactor that heats hydrogen and expels it through a nozzle, roughly doubling exhaust velocity. This is a real technology tested in the 1960s under Project Nerva, and it performs far better than chemical rockets for missions inside the solar system. Yet doubling exhaust velocity does not transform the interstellar problem. The rocket equation still dominates. A nuclear thermal spacecraft might achieve tens of kilometers per second, perhaps approaching 40 kilometers per second in optimistic scenarios. But that only reduces a 1 light-year journey from 10,000 years to several thousand. The scale of the distance barely notices the improvement. Electric propulsion, powered by nuclear reactors or solar arrays, offers higher exhaust velocities by accelerating ions or plasma to extreme speeds. These engines produce tiny thrust, but can operate continuously for long periods. Over years of acceleration, they might push a spacecraft to hundreds of kilometers per second. This is a significant step forward, shrinking the travel time across 1 light year to roughly 1,000 years, yet even this improvement leaves the journey far beyond the lifespan of any crew. Any machine or any institution capable of maintaining the mission, the problem is no longer simply propulsion efficiency, but the architecture of carrying fuel at all. That realization led to the most dramatic proposal of the nuclear era. Nuclear pulse propulsion. Instead of expelling hot gas, a spacecraft would detonate nuclear devices behind it and ride the blast waves forward, each explosion transferring momentum to a massive pusher plate. This concept, studied in Project Orion, offered effective exhaust velocities far beyond conventional engines. In principle, a nuclear pulse vehicle using fusion devices could reach several percent of the speed of light, reducing a 1 light-year crossing to decades instead of millennia. For the first time, interstellar travel began to look compatible with a human lifetime. But the engineering scale is immense, requiring thousands of nuclear devices, enormous shielding, and a spacecraft massing hundreds of thousands of tons. The idea is physically plausible, politically difficult, and technologically daunting, sitting at the edge of what nuclear engineering might achieve. What emerges from these propulsion concepts is not a single breakthrough, but a pattern. Chemical rockets crawl. Nuclear thermal engines improve efficiency without transforming the problem. Electric propulsion trades thrust for endurance. And nuclear pulse systems finally approach useful interstellar speeds at the cost of extraordinary complexity. Each step forward demands more energy, more mass, and more engineering ambition. The rocket equation remains in the background, shaping every design, ensuring that as long as a spacecraft must carry its own propellant, the climb toward relativistic speed becomes increasingly steep. Every propulsion system considered so far shares the same structural burden. The spacecraft must carry its own energy, chemical fuel, nuclear fuel, fusion pellet, all of them add mass, and that mass must be accelerated along with everything else. The rocket equation punishes this architecture relentlessly. The obvious escape is to leave the energy behind and push the spacecraft remotely. Instead of carrying fuel, the vehicle becomes a lightweight object driven by an external beam, and suddenly the exponential penalty of onboard propellant disappears. This is the conceptual leap behind beam propulsion and in its most ambitious modern form. The breakthrough starshot proposal. The physics is straightforward. Light carries momentum, and when photons reflect off a surface, they transfer that momentum to it. Under ordinary circumstances, the effect is tiny. But if an intense beam of light is focused onto a highly reflective sail, the accumulated momentum becomes meaningful. The spacecraft carries only a thin reflective sail and a miniature payload, while a powerful laser array located near Earth provides the energy because the power source never moves. Its mass does not enter the rocket equation. The spacecraft can therefore be accelerated to velocities far beyond what conventional propulsion allows. Breakthrough Starshot proposes using a phased array of lasers producing roughly 100 gigawatts of power, focused onto a sail only a few meters across. Attached to that sail would be a payload weighing only a few grams, essentially a microchip with a camera, sensors, communication laser, and power source. Under this intense illumination, the sail would experience enormous acceleration, thousands of times Earth's gravity, for several minutes. During that brief acceleration phase, the probe could reach approximately 20% of the speed of light, around 60,000 kilometers per second. At that velocity, 1 light year would take about 5 years to traverse, transforming interstellar distance from a multi-millennial journey into something resembling a long-duration research mission. The elegance of this idea lies in how it bypasses the rocket equation entirely. The spacecraft carries no propellant, no heavy reactor, no massive engine. It is pushed purely by momentum transferred from photons. The faster it moves, the less fuel it needs, because the fuel is not on board at all. In principle, this architecture opens a path toward relativistic travel using known physics. The speed is high enough to reach nearby stars within decades, and the technological components, lasers, optics, microelectronics, already exist in early forms. Yet the simplicity of the physics hides extraordinary engineering demands. The laser array must combine the output of millions of emitters into a coherent beam with nanometer precision. Any slight phase mismatch spreads the beam and reduces acceleration. Atmospheric turbulence, thermal distortion, and mechanical vibration all threaten coherence, meaning the system would require adaptive optics operating at unprecedented scale. The sail itself must reflect more than 99% of incoming light, because even tiny absorption would vaporize it under gigawatt level intensity. At the same time, the material must be only hundreds of nanometers thick, weigh a few grams, and survive accelerations exceeding 10,000 times gravity without tearing. Even if the acceleration phase succeeds, the mission enters a new set of constraints. The beam can remain focused only for a limited distance, meaning acceleration must be completed within minutes. After that, the probe coasts without propulsion, unable to correct its trajectory significantly. At 20% of light speed, the spacecraft would pass any target extremely quickly, collecting data during a brief flyby lasting minutes. There is no practical way to slow down, because deceleration would require another laser array positioned at the destination. Communication presents another challenge, as the tiny onboard transmitter must send data back across light years with extremely limited power. Interstellar space itself becomes hazardous at these velocities. Even sparse hydrogen atoms strike the probe with energies comparable to particle accelerator beams. Dust grain, microscopic and normally harmless, become destructive projectiles. The spacecraft must survive continuous bombardment while maintaining the integrity of its sail and electronics. The faster the probe travels, the more severe these impacts become, turning the interstellar medium into an environment that gradually erodes the vehicle. Beamed propulsion, therefore, changes the character of interstellar travel rather than solving it outright. It replaces heavy spacecraft with ultralight probes, replaces onboard fuel with distant infrastructure, and trades maneuverability for speed. The concept pushes velocities into a regime previously unreachable but it does so by narrowing mission capabilities and imposing precision requirements that stretch current technology. The idea remains physically sound, technologically ambitious, and constrained in ways that shift the challenge from propulsion mass to engineering scale and control. If beam propulsion reduces the mass of the spacecraft, fusion and antimatter attempt the opposite strategy: increase the energy density so dramatically that carrying fuel becomes viable again. The logic is simple. Chemical reactions release tiny amounts of energy compared with nuclear processes, and nuclear fission itself is modest compared with fusion. When light atomic nuclei merge, a fraction of their mass converts directly into energy, producing exhaust velocities far beyond anything achievable with chemical or thermal engines. In principle, this allows a spacecraft to reach significant fractions of the speed of light while still carrying its own propellant, avoiding the need for massive external laser infrastructure. One of the most detailed fusion starship concepts ever studied was Project Daedalus, developed by the British Interplanetary Society in the 1970s. The design relied on inertial confinement fusion, igniting small pellets of deuterium and helium, 3 using high-energy electron beams. Each micro-explosion would produce a burst of plasma directed by magnetic fields to generate thrust. By repeating this process hundreds of times per second, the spacecraft would accelerate continuously for several years, eventually reaching roughly 12% of the speed of light. At that velocity, 1 light year could be crossed in under a decade, placing interstellar travel within a time frame that begins to resemble a single professional lifetime. The scale of the Daedalus vehicle, however, reveals the cost of this performance. The total mass was estimated at tens of thousands of tons, with the overwhelming majority devoted to fuel. The helium 3 requirement alone posed a staggering challenge. This isotope is extremely rare on Earth, meaning it would need to be harvested from the atmospheres of gas giants such as Jupiter or Saturn. Before the Starship could even be assembled, humanity would need to deploy robotic factories floating in the upper layers of a giant planet, extract trace gases, refine them, and launch them into orbit for transport. The propulsion system itself becomes only one component of a much larger industrial effort spanning the solar system. Later studies explored alternative fusion fuels, such as deuterium reactions, which are easier to source but harder to ignite and less efficient. These designs typically produced lower exhaust velocities, resulting in cruise speeds of 5 to 10% of light speed. Even at these reduced velocities, crossing 1 light year would still require roughly 10 to 20 years. This is dramatically shorter than chemical or nuclear thermal propulsion, yet still long enough to impose major constraints on reliability, life support, and mission planning. Fusion starships move the problem into a new regime, but they do not eliminate the underlying difficulty of sustaining complex systems for decades in deep space. Antimatter propulsion pushes energy density to the theoretical maximum. When matter and antimatter meet, they annihilate completely, converting their entire mass into energy. No other process releases more energy per kilogram. A spacecraft powered by antimatter reactions could, in principle, achieve exhaust velocities approaching relativistic levels, enabling rapid acceleration and potentially reducing 1 light year journeys to years rather than decades. The appeal is obvious. Enormous energy, small fuel mass, and a propulsion system that operates near the limits permitted by physics. The difficulty lies in production and storage. Antimatter does not exist naturally in usable quantities and must be manufactured in particle accelerators. The total amount produced by all human technology amounts to far less than a microgram Producing even 1 gram would require energy far exceeding the output of modern power grids, and storing it safely demands electromagnetic traps that prevent contact with ordinary matter. Any containment failure would result in immediate annihilation. Scaling from laboratory experiments to kilograms of antimatter involves leaps in engineering that currently have no practical pathway. More speculative ideas attempt to bypass fuel entirely by collecting material from interstellar space. The Buzot ramjet, for example, proposes using a massive magnetic field to scoop hydrogen atoms from the interstellar medium and feed them into a fusion reactor. In theory, the spacecraft accelerates continuously without carrying fuel. In practice, the interstellar medium is so sparse that the drag created by the collection system likely exceeds the thrust produced by fusion. The concept remains intriguing but unresolved, highlighting how the scarcity of matter between stars complicates even the most imaginative designs. Across these extreme propulsion concepts, a consistent pattern emerges. Fusion offers high performance but requires industrial-scale infrastructure. Antimatter promises extraordinary energy density but demands technology far beyond current capabilities. Ramjets remove fuel mass but depend on an environment that may be too thin to sustain them. Each idea pushes interstellar travel closer to feasibility while introducing new dependencies on energy production. Materials, science, and long-duration reliability. The distance of 1 light year remains unchanged, yet the machinery required to approach it grows increasingly ambitious, shifting the challenge from propulsion physics toward the scale of civilization capable of building such systems. Up to this point, velocity has behaved like a straightforward quantity. Double the speed and the travel time halves. Increase propulsion power, and the destination moves closer. This intuition holds while speeds remain small compared with the speed of light. But once propulsion concepts begin aiming for 10, 20, or 50% of light speed, the rules change. Motion at these velocities is no longer governed by Newtonian mechanics. It falls under special relativity, where time, energy, and inertia shift in ways that dramatically reshape the cost of interstellar travel. In relativistic physics, the resistance of an object to acceleration increases as its velocity approaches the speed of light. This effect is described by the Lorentz factor, which begins near 1 at low speeds and grows rapidly as velocity climbs. At half the speed of light, the factor rises modestly. At 90%, it more than doubles. At 99%, it increases by roughly 7 times. As velocity approaches light speed, the factor tends toward infinity, meaning that accelerating any mass to exactly the speed of light would require infinite energy. This is not a technological limitation, but a structural feature of space-time itself. No engine, regardless of design, can bypass it. The energy implications are severe even before reaching extreme fractions of light speed. Consider a spacecraft with a mass of 1,000 kilograms, roughly comparable to a modest robotic probe. Accelerating this mass to 10% of light speed requires on the order of 10-17 joules of kinetic energy, comparable to the annual electricity consumption of a major industrial nation. At 20% of light speed, the energy requirement rises several times higher, approaching the total yearly output of large economies. These figures assume perfect efficiency, meaning every unit of generated energy becomes spacecraft motion. Real propulsion systems waste significant fractions as heat, radiation, or exhaust losses, increasing the practical requirement further. Scaling to a crewed spacecraft amplifies the problem dramatically. A vessel capable of supporting human life for years would likely mass millions of kilograms once shielding life support, redundancy, and structure are included. Accelerating such a vehicle to even a modest relativistic velocity would demand energy comparable to many years of total global production. Deceleration doubles that requirement because slowing down requires the same energy as speeding up. A round trip multiplies it again. At this scale, propulsion ceases to be an engineering challenge and becomes a question of how much energy a civilization can realistically command. Relativity also introduces a phenomenon that appears to soften the difficulty: time dilation. As velocity increases, time aboard the spacecraft passes more slowly relative to observers at rest. At high fractions of light speed, a journey lasting years from Earth's perspective could feel significantly shorter for the crew. At 90% of light speed, time aboard the ship flows at less than half the rate measured on Earth. A 1 light-year crossing might take about a year in the Earth frame, but only several months for those traveling. At even higher velocities, the subjective duration shrinks further, making enormous distances appear manageable from the traveler's perspective. This effect changes experience, not energy. The spacecraft still requires the same kinetic energy to reach relativistic speeds, regardless of how time flows aboard. Time dilation allows the crew to age less during the journey, but it does not reduce the cost of acceleration. The universe effectively offers a trade: shorter subjective travel times in exchange for exponentially increasing energy requirements. As velocity rises, the benefit grows, but so does the price. Relativistic speeds also transform the interstellar environment into a new hazard. Even sparse hydrogen atoms encountered in deep space strike the spacecraft with enormous kinetic energy. At a significant fraction of light speed, individual atoms impact with energies comparable to particles produced in accelerators, gradually eroding surfaces and generating radiation. Dust grains become more dangerous still, as their kinetic energy scales with the square of velocity. Shielding against this bombardment requires thick protective layers, which increase spacecraft mass, which in turn raises the energy needed for acceleration. The faster the vehicle travels, the more severe this feedback becomes. Thermal management compounds the challenge. Any propulsion system operating at relativistic energies produces waste heat. Radiating that heat into space requires large radiator surfaces, which add mass and structural complexity. As speeds climb, the power levels involved grow so large that managing heat becomes as difficult as generating thrust. The spacecraft must simultaneously accelerate, shield itself, and dissipate enormous energy flows, all while maintaining structural integrity for years. Relativity therefore reshapes interstellar travel in two opposing ways. It compresses travel time for the crew while expanding the energy budget required to achieve those speeds. It offers the possibility of crossing light years within a human lifetime, but only by demanding resources on a scale far beyond conventional engineering. The closer a spacecraft pushes toward light speed, the more the geometry of space-time itself resists further progress, converting ambition directly into energy requirements that rise without bound. By the time propulsion concepts reach relativistic speeds, the discussion stops being about engines and starts being about civilization itself. Every method capable of crossing a light year within a human lifetime requires energy on a scale far beyond what a single nation or even a single planet at its current technological level can easily provide. This is where the Kardashev scale becomes useful, not as science fiction classification, but as a way of understanding what kind of society could realistically attempt interstellar travel The scale measures civilizations by how much energy they control. A Type 1 civilization harnesses the full energy resources of its home planet. A Type 2 civilization commands the energy output of its parent star. A Type 3 civilization operates on the scale of an entire galaxy. Humanity today sits somewhere below Type I, using only a small fraction of the solar energy that reaches Earth. When the energy requirements for relativistic travel are compared with these levels, a pattern emerges. Accelerating even a modest spacecraft to a significant fraction of the speed of light demands energy comparable to years of global production. A civilization limited to planetary energy budgets would struggle to justify such an investment, especially when multiplied by deceleration, shielding, redundancy, and mission infrastructure. For a Type 1 civilization, the same mission begins to look difficult but conceivable. For a Type 2 civilization harnessing stellar scale power, the energy cost becomes almost routine. The same journey that appears impossible for us becomes manageable for a society that can redirect even a tiny portion of its star's output. This transforms 1 light year from a distance into a threshold. It is not simply the gap between stars, but a dividing line between civilizations that remain confined to their planetary energy sources and those that expand outward to capture stellar scale power. The barrier is not intelligence or knowledge. The physics of propulsion, relativity, and energy conversion are already understood. What is missing is the infrastructure required to generate, store, and direct the necessary energy. Crossing 1 light year, therefore, becomes less about inventing new equations and more about reorganizing an entire civilization around long-term energy production. The implication extends beyond engineering. A society attempting to reach another star must commit to projects lasting decades or centuries, coordinate resources across generations, and maintain technological continuity over time scales longer than most historical institutions have survived. The spacecraft itself may take only years to cross the distance, but the infrastructure needed to launch it could require generations to build. Energy collection arrays, fusion networks, orbital manufacturing, and deep space assembly all demand sustained stability. Interstellar travel becomes an expression of social durability as much as technological capability. This perspective reframes the silence of the night sky. If intelligent life is common, the absence of visible interstellar visitors may reflect how difficult it is to cross this first threshold. Many civilizations might develop science, industry, and even planetary scale technology without ever advancing to stellar energy use. They remain technologically sophisticated, yet spatially confined, able to observe the universe, but unable to move through it. 1 light year then acts as a filter, not because it is the largest distance, but because it is the first that demands a transformation in how a species generates and manages energy. Seen from this angle, interstellar travel is not the next step after space exploration. It is a different category entirely, requiring a transition from local engineering to civilizational engineering. Rockets, sails, and fusion drives are components, but the decisive factor is whether a species can scale its energy production beyond planetary limits. The mathematics of relativity and propulsion define the cost, and the Kardashev scale describes who can afford to pay it. A light year becomes the smallest meaningful test of that capability. A distance that quietly measures whether a civilization has learned to extend its reach beyond the energy of its home world.